We introduce MVImgNet, a large-scale dataset of multi-view images, which is efficiently collected by shooting videos of real-world objects. It contains 6.5 million frames from 219,188 videos crossing objects from 238 classes, with annotations of object masks, camera parameters and point clouds. We also introduce MVPNet, a large-scale 3D object point cloud dataset derived from MVImgNet. It contains 87,200 samples from 150 categories. Compared to the existing datasets, our dataset far exceeds them in terms of the number of objects and categories. We conduct extensive studies for probing the potential of MVImgNet and MVPNet on a variety of 3D and 2D visual tasks, where our datasets demonstrate promising performances. Meanwhile, there also remains lots of possibilities for future exploration. For each video in MVImgNet, we exploit an automatic process to obtain the common 2D and 3D annotations. Given the raw video as input, we conduct sparse reconstruction by applying callmap structure for motion algorithm on a series of equal time interval chosen frames. Then we segment the foreground object by using an off-the-shelf background removing tool. Finally, we apply multi-view stereo to reconstruct the dense point clouds, which will be used to build the MVPNet. Here comes the question, what can MVImgNet do? We attempt to probe the power of MVImgNet by conducting some pilot experiments. Next, we present some representative experimental explorations. The first experiment is the generalized NERF from few-shot views. Given a few sparse view images as input, the goal is to learn a generalizable NERF model that can render novel view image. Training such a NERF model that can generalize to unseen objects requires learning 3D priors from a huge amount of multi-view images, and our MVImgNet dataset perfectly fits this demand. Specifically, we select IBRNet as benchmark method. We first pre-train IBRNet on the full MVImgNet dataset. Then fine-tune on the training datasets used in IBRNet for a few iterations. And compare with the original train-from-scratch IBRNet model in terms of generalization capability. The quantitative results presented in the table show that pre-training on MVImgNet improves the generalization ability of the model by a large margin. And we also show the qualitative results before and after using MVImgNet, which also validate the benefits of our dataset. The second representative task is the view-consistent classification. Although humans can easily recognize one object from different views, deep learning models can hardly do that robustly. Given different viewpoint images of the same object as input, a robust classification model should output the same class prediction with high confidence. When the model predicts wrong class, we regard its confidence as 0. In this way, we can calculate the confidence variance and average to measure the multi-view classification robustness. In addition to ImgNet, we build a new training set called MVImix. By mixing the original ImgNet data with MVImgNet, we also build another two artificial training sets, namely MVIGAP and MVIAugust, that only differ MVImix with image views. We compare the variance of the softmax confidence and the accuracy on MVImgNet test set for examining the view consistency. As illustrated in the table, adding our MVImgNet data for training can effectively improve the model's view consistency and accuracy. We further provide some visual results in the following. The third representative task is multi-view stereo, which aims to reconstruct 3D geometry from multi-view images. Learning-based methods are introduced to encode the multi-view images and build a cost volume to predict the depth maps for 3D geometry reconstruction. However, these end-to-end methods require massive RGBD data for supervision, which is always difficult to acquire. We demonstrate that our MVImgNet is capable of benefiting the data-efficient MVS with limited training examples. Specifically, we pre-train a self-supervised MVS method on MVImgNet. Then, we fine-tune the pre-trained MVSNet on 5%, 15%, and 25% of DTU training samples, and evaluate on the DTU test set. The quantitative results in the tables report the error between the predicted and ground truth depth map, which indicates that the MVImgNet pre-trained model can improve the model trained from scratch by a large margin under the data-efficient setup. Here comes another question: what can MVImgNet do? We answer this question by exploring the possibility of MVImgNet on point cloud classification. We believe that future works may also utilize our dataset to help much more 3D understanding tasks, such as indoor scene parsing, outdoor environment perception, pose estimation, and robotics manipulation. We advocate paying more attention to real-world setup, which is more feasible for real applications. We show that pre-training on MVImgNet is able to aid the performance of real-world point cloud classification. In particular, we pre-train several models on MVImgNet and fine-tune them on ScanObjectNN. Compared with train-from-scratch method, pre-training on MVImgNet is able to increase the classification accuracy under most circumstances. We also exploit self-supervised learning on MVImgNet for 3D object point cloud understanding. Existing methods all pre-train on synthetic datasets, making it hard to obtain rich real-world representations. By pre-training point MAE on our MVImgNet, it outperforms the state-of-the-art methods when fine-tuned on ScanObjectNN, proving the benefit of MVImgNet on the self-supervised learning regime for real-world point cloud classification. That's all about this presentation. For more details, you can refer to the home page and paper. Thanks for your watching.